Hi everyone, this is Mingyao. In this video, I'll be looking at how to simulate a laser powder bed fusion process. This is a 3D printing process. We're going to simulate the process of laser powder bed fusion, which is using fusing powders of metal with lasers to make very complex shapes. Ansys has made this extremely easy to do, so let's give it a try. I'm going to start with this nozzle geometry, and in the custom analysis system section, we have two options: laser powder bed fusion, thermostructural, or inherent strain. Thermostructural actually models the thermal process of during the laser powder bed fusion process, and using that temperature to calculate the inherent strain as we build up the part. So we're going to model the deposition of the 3D printing process layer by layer in this analysis. I'm going to start up Ansys Mechanical. We're going to run some analysis. Okay, here's our model. It's important to make sure that the model is oriented. The build direction is in the z-axis. This makes the simulation easier. I'm modeling the base plate as well as the part I want to print. So there is a very helpful add-on called Laser Powder Bed Fusion Setup Wizard. So we're going to use this add-on to do our analysis. Super easy. Select the part. This is the part we want to build. We are not including any support geometry, and this is the base part. There's no non-build geometry to be included here, no powder geometry, no symmetry defined. So that you can see it's setting up my analysis as we go. Have a few different options for meshing. The easiest, fastest one is to do a voxelized part. So I'm going to, depending on the build height in the build process, you can see that it gives you a lot of description on what the different type is, what different types of meshing can be used. There's Cartesian, layered tetrahedra, which gives you closely match the geometric shape, or voxel, which is fast and reduces with reduced material property to do fast analysis. Element size is determined by the mesh height, etc. So I'm going to specify some sizes based on my model here. Generate the mesh, and let's go. Okay, so you can see it's created voxels for the part I'm building as well as the base here. You can select the material. Ansys has a wide range of commonly used materials, so let's build Inconel on stainless steel, including nonlinear effects. You can add additional materials as well. Using inherent strain would allow you to put in a strain temperature, but here we're going to not use inherent strain, which means we're going to deposit this model, put in the deposition thickness and actually model the deposition of the voxel layers. You can see there's a lot of machine settings for the deposition thickness, hash spacing, scan speed, how long to wait between layers, dwell time, as well as the number of heat sources. So you can change any of these. I can go from 1 to 2 or 4 if I wanted to. I can adjust the scan speed. I can reduce the dwell time or time between layers to 5 seconds, for example. So let's change some of these, make it hot. Build condition, you can specify your preheat temperature, gas flow temperature, your convection coefficient, powder convection coefficient, cool down information, removal. Do you want to do heat treatment or base removal? For base removal, you have the option of instantaneous or directional removal. So I'm going to do instantaneous. And we're going to look at the distortion of the part after it's been removed from the base. With the amount of power these things generate, the part is typically welded to the base, so we want to see what the shape is. Thermal boundary conditions. So this is a base thermal boundary condition, so we're going to say that we're going to heat up the bottom of the base, or we can select multiple surfaces like this and assign all of these areas to the base temperature. Structural, so let's say we're going to fix this part. We want to specify 3 points so that the part doesn't go fly off into space for being under constraint in a static analysis. So you can just pick any three nodes on the part itself. You can see when I switch to node select, I can pick the nodes that I want. So any node would do. Additional setup gets completed. You can choose to set up calibration or not. It tells you some information about how to do calibration. This will obviously make the simulation more accurate. Calibrate it to your particular machine. Go ahead and finish this. And that's it. So that's all you need to do to model laser powder bed fusion process to look at the deformation shape. We have a number of options for correction as well, or add-ons. There's distortion compensation. So if you want the shape such that after the printing stops and when you cut it off, you want it to distort to the shape you want, you can do a whole distortion compensation. I'll show that another day. You can see there's a number of other options. In addition to the laser powder bed fusion process, we also have a direct energy deposition as well as a sintering simulation. But without further ado, let's go ahead and run the simulation on my laptop using 4 cores. So small simulation. As your model gets larger with smaller features, you'll need smaller voxels. That'll certainly benefit from having a larger simulation workstation. We're going to execute the transient thermal first, and then you'll do a series of static structural simulations to look at a deformed shape. Okay, once the simulation has completed, you get this type of results where you can look at the build-up process for the thermal analysis. You can see we're heating up layer by layer, looking at the temperature and residual temperature as you build up the part. There's a build-up step and a cool-down step. On the structural deformation side, you can see the amount of residual distortion is 0.6 millimeters. If I look at the way this is built up, you can see the build-up process with the residual deformation, the cool-down step, finally the removal of the base. We can look at things like stress and any other quantity of interest, stress, strain, etc. Again, building step, followed by cool down, followed by base removal. So that's a quick demonstration of how we can set up a laser powder bed fusion additive manufacturing simulation predicting residual distortion. As I mentioned earlier, we're able to also take that many steps further by looking at the additive process, generating STLs. We can look at distortion compensation and a variety of other techniques. Some of those I'll show in later videos. If you like this video, please subscribe to our YouTube channel. Otherwise, have a great day. Thank you.